Hi everyone, my name is Mats Kaimberg and I'm working at ABB Distribution Solutions in Vaasa, Finland as a trainer for our protection relays and protection relay applications. The topic for this webinar is transformer differential protection. So here's the content for this webinar. We will start with an introduction where I will bring up what type of faults can occur in a power transformer and what is causing these faults. I will also show what transformer protection relays we have available from ABB Distribution Solutions. Then we will take a closer look at differential protection, how it works, and how to calculate settings. We will also look at how we use Inrush and overexcitation blocking together with differential protection. In the last part of this presentation, we will look at how we use overcurrent and earth fault protection for protecting power transformers. And finally, we will end up with a summary. So let's start by looking at what is causing faults in a power transformer. So during overheating of the power transformer, the aging of the insulation materials for windings will speed up, which will decrease the insulation level. So in practice, this would mean that over time, there will be a higher risk of short circuits between the winding turns, for example. And when there's a short circuit downstream, there will be a high current flowing through the power transformer. The high current will cause a mechanical stress on the windings, which in turn will have a negative impact on the winding insulation. Faults can also be caused by overvoltage due to, for example, lightning strikes or when a big load is disconnected. In oil-filled transformers, the oil is used as an insulator and for cooling of the transformer. The insulation level of the oil reduces due to contamination, which can be the result from, for example, overload situations where winding temperature gets high, or in case of partial discharge in the winding insulation. As the oil insulation level reduces, there will be a higher risk of flashovers, for example, during overvoltages. So let's then have a look at where in the transformer we can expect to have faults. So like you can see here in this picture here that most of the faults will occur here in the on-load tap changer. This is due to the fact that the on-load tap changer have many mechanical parts. And looking forward here, we can see that also a quite big part of the faults will happen also in the windings. And we will also have faults related to tank and oil and bushing as a quite big portions also of all the faults. So what we need to have then is a protection device that can detect and clear these faults quickly. Let's then take a look at what type of electrical fault types we can expect to have inside the power transformer. So first of all, we can have winding short circuits. That means flashovers between windings. There can be interturn faults which means that there's a flashover between the winding turns. And then we can have short circuits. It can be also outside the winding where this is happening. Or we can also have earth faults between the winding and the tank, for example. So when a fault happens, for example, like in this picture here, where we have a interturn fault in the winding, the fact is that repairing will be very expensive and time consuming, since this is something that cannot be done on site. But to limit this kind of fault, so we don't end up with more damages to the power transformer, we need to have a protection that it is sensitive and reliable and clears the fault as quickly as possible. For this, we have different protection relays available from ABB Distribution Solutions. So the protection relays, what I have here is from the Relion family. So first of all, we have from the 615 series, the RET and RED 615. Now the difference between these two relays is that the RET is a transformer protection relay and the RED is a line differential relay. Now the reason why I have brought up RED here is because the line differential relay can also protect a power transformer together with its line differential protection. So if you want to learn more about line differential protection, we have a webinar available on that topic. Next, we have the RET 620. And the main difference here between RET 620 and 615 is that first of all, we have more IOs available in this relay. But the other thing is that this relay can also have a voltage regulator functionality in the same relay. So we can have both transformer differential and voltage regulator in the same relay. So, and again, if you want to learn more about voltage regulation, we have also a webinar on that topic. Next, we have the RET 630 and the REX 640. So generally, we can say that the difference between these relays are that if you go here from the top to the bottom, so the bigger transformer you have, the more protection functions you need to have to be able to protect the transformer properly. So the 615 series and 620 have less protection functions related to transformer protection, where RET 630 and 640 have more protection functions available. And one other thing I would like to point out here is that in REX 640, we can also protect the 3-winding power transformers. In addition to protection relays, we also have other devices protecting our power transformer. So, for example, a gas relay, a Buchholz relay, which is located here between the main tank and the conservator tank. And the purpose of the Buchholz relay is that when there are some flashovers in the power transformer, a gas will be generated, and this gas will flow here into the Buchholz relay and get trapped here inside. So this gas, it can then be taken out from the Buchholz relay and analyzed, and based on what type of gases we have, we find we can say that how big risk is there that we will have a failure in the power transformer. More devices we can have is thermometers for measuring the oil temperature or the winding temperature. We also can have a on-load tap change pressure relay, and for overvoltage situation we have a surge caps or surge arresters and so on. But in generally, when we look at from the protection relay perspective, we can say, like we have here in a typical example, that since we are measuring the current here from both the high voltage and low voltage side, we use different protections for these current measurements. So from the high voltage side, first of all, we will have usually overcurrent protection, a low and an instantaneous stage. We can also have a thermal overload protection, over and under voltage protection, and also over residual voltage protection. And as you can see here in this picture, we have a star connected winding here on the high voltage side. So for this, we can also apply earth fault protection by means of non-directional as a backup, or then we can have restricted earth fault protection for protecting the winding on the high voltage side. On the low voltage side, we usually have overcurrent protection as well, both low and instantaneous stages. Now, since we are measuring the current from both sides of the power transformer, we also can apply differential protection. And we can also have, if we have some temperature sensors available, we can connect these to our protection relay to measure oil temperature. Now the oil temperature can then be used for alarm purposes, or it can also be used for protection purposes. So let's then have a closer look at the differential protection for power transformers. So first of all, we will look here at some advantages of the differential protection. So the differential protection, it consists of a stabilized stage and an instantaneous stage. And as you can see here, we have quite fast operate times, where we have 40 milliseconds for the stabilized stage and 20 milliseconds for the instantaneous stage. And since we are calculating the difference between the current flowing into the transformer and what is flowing out, we will have a very sensitive protection. And generally speaking, differential protection, it can be used in many different applications. I will show that in the next slide here. And since we are measuring the current on both sides of the transformer, it means also that we have a predefined protection zone here, which is between the current transformers. So we can say that we have an exactly defined protection zone here, which means that it will only operate for faults here inside and not be stable for faults outside the protected zone. Coming to the disadvantages with differential protection, it requires higher CT requirements than for example, for overcurrent protection. And we always need to have a backup protection, which we normally use overcurrent protection for. So let's then have a look at in which application areas we can use differential protection in general. Well, first of all, as this topic explains about, we use differential protection for protecting power transformer. It can also be for protecting lines, but we can also use it for protecting motors and generators, and also a combination of a generator transformer bank, where we are protecting both the step-up transformer and the generator. So let's then have a look at the basic principle here of the differential protection. So as I mentioned, the basic principle here is that we are calculating the differential current. So what flows into the power transformer should also flow out. Now, the differential protection in Reliance series, it's always looking towards the protected object, which is our power transformer. So that's why we have a plus sign here when calculating the differential protection. But generally, we can say that in a normal situation, the differential current calculated should be 0. We are also calculating a bias current, which is the average of the sum of the high voltage and low voltage side currents. So looking at the bias current in normal situations, it should be same as the load current. Let's then have a look at the protection operation characteristic that the differential protection is using. So we are using this kind of stabilized differential protection here. And it consists of 3 different parts that you can see here. So looking at this characteristic in this diagram, we can see here on this axis, we have the differential current, and here on this axis, we have the bias current. And from that, we can then see that during low load current, we tolerate only a small differential current, since the protection will operate as soon as the differential current exceeds this stabilized stage here. And as the load current increases, or let's say the bias current, we will tolerate more differential current. We will shortly come into this topic, that why it is like this. In addition to the stabilized stage, we also have the high operate value here, which means that as you remember here, that we have a faster operation here, 20 milliseconds, if the differential current exceeds the high operate value setting here. So let's then have a look at the different scenarios here. So in case we have a fault in the power transformer, or let's say inside the protected zone, that means that we will have a high differential current. And looking here in this picture, so the differential current will be about here in this diagram then. In case we have a fault outside the protected zone, let's say we have a downstream fault, it means that there will be a high current flowing through the power transformer, but in that case, we shouldn't operate. So in such kind of situation, we can expect that we will have a high bias current, but a smaller differential current. The differential current will not be zero here due to that there will be some measuring errors in the CTs, and there can also be some partly saturated CTs which will lead to that the protection will measure a difference current. And then in a normal situation, then we are below the stabilized stage and somewhere around here. So the differential current will be very low, and also the bias current will be then according to the load current. So looking at this picture here, we understand then that the stabilized stage will provide a stabilized differential protection, and that means it will give us both sensitivity and also stability during outside faults. Looking then at the different settings for the stabilized differential stage. So the first setting we have here is the low operate value. And when defining the setting for the low operate value, we should consider CT errors and varying tap changer position. In Reliant relays, it's also possible to compensate for the tap changer position because when the tap changer is changing position, it's also changing the number of effective winding turns, and this will naturally then cause a differential current. So what you can do here is you can bring the tap changer position information to the differential protection, and it will then automatically compensate for the differential current caused by the different tap changer positions. We should also include transformer no load current and also some over-magnetization currents. And the setting range for the low operate value, it's between 55 to 50%. Normally, when we calculate the settings, we will have a value that is about 20% for transformers and 5% for generators. Now, the end section 1, so that is the point here when the slope starts in this characteristic. And this slope, it's called slope section 2. So the end section 1 is fixed in transformer differential protection to 0.5 times nominal. So this means half of the rated current of the power transformer. So when we calculate then the settings for slope section 2, we should include then CT errors and also again tap change the position differences and so on. So the expected, or let's say the setting range for this slope section 2 is 10 to 50%. For end section 2, which is where the slope section 2 starts and slope section 2 ends and slope section 3 starts. It's adjustable, but mainly we are using a recommended setting as 1.5 for transformers. For generators, it's between 1 and 1.5, and for 1.0 for motors. Let's then have a look at what kind of advantages we have in numerical relays. So looking at this setup here, you can see that we have our power transformer here and the main CTs on both sides, but we also have an interposing CT here from on one side. And what is the reason to this? Well, let's have a look here at this setup here. So what we have here now is a power transformer, which is on the primary side, we have 115 kV and 20 kV on the secondary side. It's a 75 MVA transformers, and on the primary side we are using then 400 to 5 CTs, and on the secondary side 2500 to 5 amp CTs. So the problem comes here when we calculate that what will be the secondary currents at rated load. So the secondary current, that is what our relay here is measuring. So that will then end up to 4.7 amp on the primary side and 4.3 on the secondary side. So you see that because the differential protection is calculating the differential current, so it will not be zero here. So what was done with all the protection relays, that was that we were using an interposing CT here to correct for this current difference between primary and secondary side. So it will then be same current coming from both sides. But in modern relays, we don't need to have an interposing CT because this is done with a setting. So what you can do is, what we have is a setting for compensating then for the current differences here between the primary and secondary side. So what this means in practice is that if you are changing the protection relay from an old one to a new one, and you have an interposing CT, so what you can do then is remove the interposing CT because it's not needed anymore. We can do the CT ratio correction with a setting in our new relay. Same situation can also be the fact when we have, like in this example, a power transformer which is YND11. So this means now that when we have a star connected winding on the primary side and a delta connection on the secondary side, there will be a 30-degree phase shift between primary and secondary side. So again, in all the relays, we had to compensate for this 30-degree phase shift, and that was done by using an interposing CT, like in this example, a YND5 interposing CT. But again, since this can now be done with the settings in the relay, telling the protection that what type of windings we have in the power transformer, we don't need the interposing CT anymore. Then we have the situation here where we have a earthed star winding, and we have a earth fault outside the protected zone. So what will happen then is that there will be an earth fault current flowing here in one phase. And this earth fault current, it will not then be seen in the same phase here on the other side of the power transformer. So what will happen then is the differential current, differential protection will see this as a differential current and operate. So in modern relays, we can eliminate this so-called zero sequence current with help of a setting parameter. So overall, looking at what is happening inside the protection relay now for when looking at the differential protection. So it's not directly measuring the current coming from the CTs. We understand that it's first doing, if needed, a CT ratio correction. It's also doing a vector group matching in case we have different winding types in the power transformer. It's also doing a zero sequence elimination. So after that, the differential and the bias current is calculated, and the operation is based on those measurements. So the takeaway with this is that if you're replacing an old relay with a new one, we don't need to use the interposing CTs anymore, so they can be removed. Let's then have a look at the setting calculation example. So what we will go through here is first calculate the CT ratio correction setting for this setup we have here. We will calculate the differential operation characteristic. We will set the correct vector group matching and also a setting for the CT connection type. So to be able to calculate the CT ratio settings, you can see here's a formula for calculating it. We first of all need to know that, okay, what is the nominal current of our CTs, and that we can see here from our picture. But we also need to know that what is the nominal current of the power transformer. And that is what we need to calculate first. We calculate the nominal current of the power transformer on both sides, like this. And then after that, we can put these values into this formula. And we get a CT ratio correction factor here for winding 1 to be 2.29, and for the winding 2, 1.45. So this is how the CT ratio correction is calculated. instead of using interposing CTs. Then we can go and calculate the operation characteristic. And we always start here by with the slope section 2. So here we include then the rated accuracy of the CTs, tap changer position range if it's not compensated, the accuracy of the relay, and the safety margin. Then after that, we can calculate the low operate value, and we do that by taking 0.5 times the result we get from the slope section 2 calculation, and then plus 10%, which is for the no load losses in the transformer. And this allows for some overexcitation in the power transformer. For end section 2, we use our recommended setting, which is 1.5. So with numbers, this would then look like this. So we take the rated accuracy for our CTs. We can see here that we have a 5P20 15 VA CTs on both sides. So we use this 5 here on both sides. And in case we are not compensating for the tap changer position, we can see here that we have a tap changer which have a 6 position up and 6 positions down, and each step is 1.67%. So if we are not compensating for the different tap changer position, we need to include also 10% differential current here. Then we add 3% for the accuracy of the relay and a 4% margin. So the result for slope section 2 will be 17%, or if we are not compensating for the tap changer position, then we need to set it to 27%. Then we can go to the low operate value, and here we use then the result we get from the slope section 2, 0.5 times 17% plus the 10%. And our setting will then be 19%. So you can see here that if we are not compensating for the tap changer position, then we will have a less sensitive protection. And end section 2 will be the recommendation of 1.5. So then we have the characteristic calculated. Then after that, we need to tell the differential protection also what kind of power transformer we have, what kind of windings we have. So this way we don't need to use any interposing CT for that purpose. So in this case, we have a YND11, and this is done then with separate settings for both windings. So we have for winding type 1, we set to YN, and for winding type 2, we set it to D. And the clock number, we also have a setting for that, and that will be 11. And from the technical manual, you can also look from this kind of table where it describes different type of power transformer and windings. So like in this example now that we have here, we can locate now the YND11 transformer. So then you can directly read that, okay, which setting do I put for winding 1 type and for winding 2 type and for the clock number. This table also tells you if we need to activate the 0 sequence elimination, and in this case it's not needed. And then finally we have the CT connection type setting. And the purpose of the CT connection type setting is that it tells how we have connected the secondary circuit between our CTs and the relay. So the setting can either be type 1 or type 2. And if we look at what is the difference here now. So let's first look at this type 1. So in this case, the current will then flow to the N input on the relay and out on the 1/5A input. That's for the primary side. And for the secondary side, the current will flow in on the 1/5A input and out on the N. So you see there's a difference here between these two. So basically it's 180 degrees phase shift. So if your connection is like this, you choose type 1. On the other hand, if the current flow in on 1/5A on both sides, then you choose type 2. So the difference between these two settings is that the protection will turn the current measurement 180 degrees, depending on which setting you are using. When we are energizing a power transformer, there will be so-called inrush current. And this inrush current, it's a magnetizing current, which then will only be seen on one side of the power transformer. So it will be seen on that side that is energized. And if we look at the waveform of the inrush current, it looks something like this, like in this picture here. And since it's only seen on one side of the power transformer, it will then also be seen as a differential current by the protection. And the inrush current, it can be many times the rated current. So it's not a small current, it's quite a big current we can expect. And it can last up to several seconds for bigger power transformers. Now, since it's seen as a differential current, we need to somehow block the differential protection when we are energizing the power transformer. And this can be done by using the second harmonic in the inrush current. So if we then look here at the second picture here, we can see that the inrush current, the main part of it consists of the fundamental component. But there's a quite big component, second harmonic component also available here in the inrush current. So what we can do here is use this, measure this second harmonic, and if it's available in the current measurement, then we block the differential protection. And it is done in this way that first of all, we calculate the ratio of the differential current for the second harmonic and the fundamental component. And this is done for each phase separately. Then after that, we use this value and calculate a weighted average for each phase separately. So if the weighted average then exceeds our setting, which is normally 15%, then the differential protection is blocked. And what is important to know here also is that the high-set stage is not blocked. And this is because that we need to have some backup protection here in case there is a real fault inside the power transformer. So in that case, the stabilized stage will be blocked, but the high-set stage will clear the fault. Then in case we will have a over voltage or under frequency, the power transformer might then be over magnetized. And this will then be seen again on only one side of the power transformer. And that's why we also need, it will be seen also as a differential current. And that's why we also need to block the differential protection. Now, how can we detect this kind of overexcitation situation? Well, we can use the fifth harmonic in this case to detect the overmagnetization situation. And based on this fifth harmonic, we can then block the differential protection. So generally, a small and a short over voltage is not dangerous. But in case there is a higher over voltage, there is always a risk of insulation failures. But the differential protection should not take care of this kind of situation. It should be stable. So we need to somehow then block differential protection during this kind of situation, and that is done by using the fifth harmonic blocking. And in case there's a high over voltage, which will then lead to a higher overmagnetization of the power transformer, the content of the fifth harmonic will then also increase. So in this kind of situation, it means that the voltage is probably too high. And there we have now the possibility that we can deblock the fifth harmonic blocking for the differential protection. So in case of a high over voltage, the differential protection will then operate and disconnect the power transformer. So let's then have a look at overcurrent and earth fault protection. Now, as mentioned there in the beginning, we always need to have overcurrent protection as a backup for the differential protection. And what we can use is instantaneous overcurrent protection, which we set to 1.2 to 1.3 times the maximum through fault current. And this will then give us a backup protection, which will cover about 80% of our power transformer. The low set stage must then be time coordinated with other protections. Then when it comes to earth fault protection, if we have a star connected winding, we can measure the earth fault current, and for this we can use non-directional non-directional earth fault protection. Now, the problem here is that in case we have an earth fault inside the power transformer or an earth fault outside the protected zone here, this protection cannot distinguish between internal and external faults. So that's why we use earth fault protection as a backup protection. One second alternative here is to either measure or calculate the residual current based on the current from the phase CTs. But the situation here is the same. The earth fault protection cannot say if the fault is inside the power transformer or outside the protected zone. So of course we can then utilize directional earth fault protection here, but generally directional earth fault protection is also then slower than a differential protection. So a better option is then to use the restricted earth fault protection. So the first example here is by utilizing the low impedance or restricted earth fault protection. And it works in this way that the protection is calculating the differential current between the neutral and the residual current. And this protection will then only operate for faults inside the power transformer here. It will not detect faults which are outside of our protected zone. One of the benefits of using low impedance restricted earth fault protection is that the CT ratios of the phase CTs and the neutral CT can have different ratios. As an alternative to the low impedance is the high impedance restricted earth fault protection. So basically the result is the same. Both operates only for faults inside the power transformer. The drawback here is that the ratio of the phase CTs and the neutral CT must be the same. So basically phase and neutral CTs must be identical. But in this protection principle, we are then using here a stabilizing resistor, which gives a stable protection also during CT saturations. And during a fault, the voltage here in the secondary circuit will rise quite a lot. So for that, we also have here a voltage dependent resistor for protecting our protection relay inputs for high voltages. So then we come to the summary. So what we have learned here during this webinar is that power transformers can have many different types of faults. And some of these faults can have evolved over a long period of time due to overheating of the power transformer or due to over voltage or to high through fault currents, which is causing stress to the transformer windings. And to detect and clear these faults, we need to have different protection devices. So, for example, protection relays are then using the current measurement from both sides of the power transformer. And with help of these current measurements, we use differential protection, overcurrent, and earth fault protection, and so on. We can detect and clear the fault as quickly as possible inside the power transformer. And to achieve then a stable and reliable protection, we need to set our protection functions according to the application we have. So with these words, I thank you very much for attending this webinar. I hope you learned something new, which you will find useful. Thank you very much.